12.7. A. Using the Bohr's model, calculate the speed of the electron in a hydrogen atom in the n equal to 1, 2, and 3 levels. B. Calculate the orbital period in each of these cases. Okay. Now see, we have the equation for speed in nth level, that is 2 pi e square upon nh 4 pi epsilon 0, or that we can write as 2 pi k e square upon nh. Okay. Now for n equal to 1, we can write V1, that is equal to 2 pi k e square, n equal to 1 into h. Now substitute all the values: 2 pi 3.14, k 9 into 10 raised to 9, e 1.6 into 10 raised to minus 19, square of it, then upon h 6.625 into 10 raised to minus 34. Then solve it, you will get the answer. Then after, for n equal to 2, n equal to 3, now directly you can use this answer of V1, because V1, that is 2 pi k e square by h. So this particular portion 2 pi k e square by h, that you can write as V1. So you can write V2, that is V1 by 2. તો અહીંયા જે આપણે V1 નો આન્સર આવ્યો by 2 કરો, you will get V2. Then again here 2 pi k e square by h, that is V1. So for n equal to 3, V3, that is V1 by 3. તો જે V1 નો આન્સર આવ્યો એને by 3 કરો એટલે આપણને V3 મળી જશે. Clear to all of you? Now see, for periodic time we can write Tn, that is equal to 2 pi Rn upon Vn. Okay. Now Rn, that is equal to n square h square epsilon 0 pi me square. But in this equation, if we substitute n equal to 1, then we will get R1, and R1 that will come to 0.53 into 10 raised to minus 10 meter, that we already discussed. So here simply we can write Rn, that is n square into R1, because this portion h square epsilon 0 pi me square, that is R1. Okay. Then here we already proved Vn, that is V1 by n, and V1. So for that, if we substitute all the values of the constants, then we will get V1, that is 2.2 into 10 raised to 6 meter per second. Actually this R1 and V1 we already calculated in one example. Okay. અહીં ખાલી એમને ફરીથી મેં મૂક્યા છે, એટલે આગળ ઉપર યુઝમાં આવે આપણને. Now periodic time in nth orbit, that is 2 pi. Now Rn, so Rn that we can write n square R1, and Vn that we can write V1 by n. It implies that time period in nth orbit, that is 2 pi n cube into R1 upon V1. So Tn, that is n cube. Now see here 2 pi Rn upon Vn. So here we will get 2 pi R1 upon V1. So this 2 pi R1 upon V1, that is nothing but T1. So we can write Tn, that is equal to n cube T1. Now calculate the value of T1 separately first. So 2 pi R1 upon V1, R1 that is 0.53 into 10 raised to minus 10, V1 that is 2.2 into 10 raised to 6, and you will get the answer here. Then after, suppose you want to calculate T2, means take here n equal to 2. So n cube, so 2 cube into T1. So take this value of T1 here, multiply it by 8, you will get periodic time in second orbit. Then take n equal to 3. So 3 cube into T1. So this one 27. Take the value of T1 from this calculated one and you will get the periodic time in third orbit. Clear to all of you? Next one, 12.8. The radius of the innermost electron orbit of a hydrogen atom is 5.3 into 10 raised to minus 11 meter. What are the radii of the n equal to 2 and n equal to 3 orbits? So R1 that is given to you 5.3 into 10 raised to minus 11 meter. And we know this thing, Rn that is equal to n square into R1. See here, we already proved Rn that is equal to n square into R1. So for n equal to 2, we can write R2 that is equal to 2 square into 5.3 into 10 raised to minus 11. Solve this one, you will get the answer. Then take n equal to 3, you will get R3 that is equal to 3 square into 5.3 into 10 raised to minus 11. Solve this one, you will get the answer. Clear to all of you? 12.9. A 12.5 electron beam is used to bombard gaseous hydrogen at room temperature. What series of wavelength will be emitted? Now the energy incident, that is 12.5 electron volt, it implies that 12.5 electron volt energy will be absorbed. Now ground state energy at room temperature, that is minus 13.6 electron volt. So if 12.5 electron volt energy is absorbed, then we will get the total energy, that is minus 13.6 plus 12.5, and you will get minus 1.1 electron volt. Okay, but this minus 1.1 electron volt, that is the energy very close to the energy in n equal to 3 state. Okay, so we can say this thing, when 12.5 electron volt energy is absorbed, then electron will jump to n equal to 3 state. Now when it jump to n equal to 3 state, then after the possible transitions are like this, from 3 to 2, then 2 to 1. And one transition is possible, 3 to directly 1. Okay. So in this way, we will get 3 spectral lines. So for 3 to 1, you will get Lyman series, as well as when it jump from 3 to 2, you will get Balmer, but again when it jump from 2 to 1, you will get Lyman series. So in 3 to 1 jump or 2 to 1, in these transitions you will get Lyman series. And for the transition from 3 to 2, you will get Balmer series. It implies that now the transition from 3 to 1. So energy difference minus 1.5 minus minus 13.6. So that is 12.1 electron volt. Now E, that is Hc by lambda. So lambda, that is Hc by E. Substitute the value of H, 6.6 into 10 raised to minus 34. C, that is 3 into 10 raised to 8. And energy, that is 12.1 electron volts. So multiply by 1.6 into 10 raised to minus 19, this much joule, and you will get the wavelength emitted. Then for the transition 2 to 1, the energy difference, so energy in level 2, that is minus 3.4, for 1 minus 13.6. So difference of these two, that is 10.2 electron volt. And now lambda, that is hc by E. Again substitute the values, you will get the emitted wavelength. Then for the possible transition of 3 to 2, you will get Bohr. So 3 to 2. So energy associated with third state, that is minus 1.5. For second one, that is minus 3.4. So resultantly you will get minus 1.5 minus 3.4, that is 1.9 electron volt. So you will get again lambda, that is hc by E. Substitute the values of hc and this E obtained, you will get the wavelength emitted. Clear to all of you? Same example is repeated by taking the energy 12.1 electron volt. So if the energy absorbed by the electron in ground state, that is 12.1, then the total energy of electron will be ground state energy minus 13.6 plus 12.1. So now the energy, that will be minus 1.5 electron volt. So now with this much energy, electron will be in which state? So that we can calculate like this. En equal to minus 13.6 upon n square. So n square equal to minus 13.6 divided by minus 1.5. So here you will get answer, that is 9. So n equal to 3. Directly you can understand, yes, now the electron is in n equal to 3 state. Okay. So when electron is in n equal to 3 state, then how many possible spectral lines can be obtained? So if the transition is from 3 to 1, then we will get second line of Lyman, second line of Lyman. Then if the transition is from 3 to 2, then we will get first line of Bohr. Then from 2 to 1, we will get first line of Lyman. And then we can calculate all the wavelengths in this way. Now here, this generalized equation, always remember, that is useful for entrance examination. Number of spectral lines obtained, that is equal to n minus 1 by 2. It implies that when electron is in nth state and when it is transited from nth state to ground state with multiple transitions, at that time the total number of spectral lines obtained, that will be n into n minus 1 by 2. See here, electron is in third state. So if we substitute here 3, then 3 into 3 minus 1 by 2. So this 3 minus 1 is 2 and these 2 cancel. Your final answer will be 3. So you will get total 1, 2 and 3 spectral lines. Clear to all of you? 12.10. In accordance with the Bohr's model, find the quantum number that characterizes the Earth's revolution around the Sun in an orbit of radius 1.5 into 10 raised to 11 meter with orbital speed of 3 into 10 raised to 4 meter per second. Mass of Earth, that is given to you. Now, radius of the orbit, that is 1.5 into 10 raised to 11 meter. Orbital speed, that is 3 into 10 raised to 4 meter per second. Mass of the Earth, that is 6 into 10 raised to 24 kilogram. Now, as per Bohr's second postulate, the angular momentum in the orbit, that is in the integer multiple of h upon 2 pi. So we can write mvr, the angular momentum, that is nh upon 2 pi. So n equal to 2 pi into mvr by h. Substitute the values 2 pi 3.14 M 6 into 10 raised to 24, V 3 into 10 raised to 4, R 1.5 into 10 raised to 11 upon H 6.625 into 10 raised to minus 34, and solve this one, you will get the orbital quantum number here. Clear to all of you? Now additional exercise 12.11. Answer the following question which you understand the difference between Thomson's model and Rutherford's model better. A. Is the average angle of deflection of particles by a thin gold foil predicted by Thomson's model much less, about the same, or much greater than that predicted by Rutherford's model? It will be about the same. Why we can say it is about the same? Because here we are talking about average angle of deflection. So when we are averaging this particular value, then it will be about same one. Then B, is the probability of backward scattering, it implies scattering of particle at angles greater than 90 degree predicted by Thomson's model much less, about the same, or much greater than that predicted by Rutherford's model? It will be much less, because in Thomson model we consider this thing, entire positive charge is uniformly distributed in the atom. There is no massive positive charge concentration at a particular position, and therefore large repulsive force is not possible in Thomson model, and therefore that will be much less. Then C, keeping other factors fixed, it is found experimentally that for small thickness t, the number of particles scattered at moderate angles is proportional to t. What clue does this linear dependence on t provide? So when the thickness is less, there are less chances for the multiple scattering. If the thickness is more, then more number of atoms will be accommodated in the path of alpha particle. So multiple scattering are possible. Clear? So here we can understand this thing, this direct proportionality of number of particles scattered to T. Then D, in which model is it completely wrong to ignore multiple scattering for the calculation of average angle of scattering of particles by a thin foil? Here in Thomson's model, we can't ignore multiple scattering, because in Thomson's model, the positive charge is uniformly distributed. So multiple scattering will take place in it when the particle is passing through the atom. Clear? So we can't ignore it. Clear to all of you? Next, 12.12. The gravitational attraction between electron and proton in a hydrogen atom is weaker than the Coulomb attraction by a factor of about 10 raised to minus 40. An alternative way of looking at this fact is to estimate the radius of the first Bohr orbit of the hydrogen atom if the electron and proton were bound by gravitational attraction. You will find the answer interesting. See here. R, that is h square epsilon 0 upon pi me square. So here take this epsilon 0 in denominator to denominator, and then after here multiply and divide this denominator by 4 pi. So we will get 4 pi square m into 1 upon 4 pi epsilon 0 e square. Okay. Now, here the Coulombian force, that is 1 upon 4 pi epsilon 0 e square upon r square. Gravitational force, that is GMEMP upon r square. Now, if we take the ratio of these two, right, then r square will be cancelled. Okay. Now here, see, it is given to you this Fg, that is 10 raised to minus 40 times weaker than this one. Okay. So we can write Fg, that is 10 raised to minus 40 Fe. So then after, here we can substitute the values. So here we can replace GMEMP. Okay, because here we want to calculate the gravitational attraction, and then the value of GMEMP, okay, that you can substitute from this comparison, or directly you can substitute the values of G, mass of electron, mass of proton, and then solve it, you will get the radius. Clear? Next, 12.13, obtain an expression for the frequency of radiation emitted when a hydrogen atom de-excites from level n to level n minus 1 for large n, so that this frequency equals the classical frequency of the revolution of the electron in the orbit. Now see, we have the equation for frequency, that is me4 upon 8 epsilon 0 square h cube into 1 upon nf square minus 1 upon ni square for the transition from ith state to fth state. Clear? Now here we have to take the transition from nth level to n minus 1th level. So in this particular equation, substitute NF equal to n minus 1 and Ni, that is n. So we will get finally the equation F equal to Me4 8 epsilon 0 square h cube 1 upon n minus 1 whole square minus 1 upon n square. So this multiple constant, that is as it is, and here now take cross multiplication, and here we will get n square into n minus 1 whole square in denominator, in numerator minus n minus 1 whole square plus n square. Again the constant in the multiple of this bracket will as it is. Simplify this one, minus n square plus 2n minus 1 plus this n square upon n square into n minus 1 whole square. So n square cancelled. Again, we can write F equal to Me4 upon 8 epsilon 0 square h cube into 2n minus 1 upon n square into n minus 1 whole square. Now here in question it is given to you for large n. So if n is very large, then 2n minus 1, that you can write nearly equal to 2n. And this n minus 1, that nearly equal to n. So now replace this 2n minus 1 by 2n and this n minus 1 by n. So we will get Me4 upon 8 epsilon 0 square h cube into 2n upon n square into n square. So 1 n here cancelled. So finally we'll get Me4 8 epsilon 0 square h cube into 2 by n cube. So here 2 by 8 will give you 1 by 4. So resultantly we have the frequency, that is Me4 upon 4 epsilon 0 h cube n cube. Now, frequency in nth orbit, that we can write speed, that is Vn, and the circumference means the distance of nth orbit, that is 2 pi Rn. Okay. Now 1 upon 2 pi as it is, then substitute Vn. Vn, that is 1 upon n is square upon 4 pi epsilon 0 1 upon h upon 2 pi. And now Rn. So here if we substitute Rn, then that is n square h square epsilon 0 upon, but that we can write in numerator pi me square. Now here cancel out which are cancelled. Then finally you will get the frequency, that is equal to me4 upon 4 epsilon 0 square h cube n cube. So this particular frequency of revolution of the electron in the nth orbit and this particular calculated frequency for the transition from nth orbit to n minus 1th orbit, both are equal. Clear to all of you? Next, 12.14. Classically, an electron can be in any orbit around the nucleus of an atom. Then what determines the typical atomic size? Why is an atom not, say, 1,000 times bigger than its typical size? The question had greatly puzzled Bohr before he arrived at his famous model of the atom that you have learnt in the text. To simulate what he might well have done before his discovery, let us play as follows with the basic constants of nature and see if we can get a quantity with the dimensions of length that is roughly equal to known size of an atom, 10 raised to minus 10 meter. A. Construct a quantity with the dimensions of length from the fundamental constants E, M, E, C. Determine its numerical values. Now see here, using E, M, E and C, you will not be able to determine the dimensions of length. Any type of combination of E, M, E and C will never give you the dimensions of length. Here you have to include epsilon 0. Then by the equation E square upon epsilon 0 mc square means for this type of combinations of four constants E, epsilon 0, m and c, you will get the dimensions of length. And in this manner, when we take the combination of these four constants, then after, by substituting its values, if we calculate the numerical value of this combination, then it will come to about 10 raised to minus 15 meter. That is very less compared to the size of atom. Then question B, you will find that the length obtained in A is many orders of magnitude smaller than the atomic dimensions. Further, it involves C. But energies of atoms are mostly in non-relativistic domain where C is not expected to play any role. This is what may have suggested Bohr to discard C and look for something else to get the right atomic size. Now the Planck's constant h had already made its appearance elsewhere. Bohr's great insight lay in recognizing that h, me and E will yield the right atomic size. Now construct the quantity with the dimensions of length from h, me and E and confirm that its numerical value has indeed the correct order of magnitude. Again here, By the combination of H, Me and E, you will never get the dimensions of length. Again, here you have to include epsilon 0. Now, with the help of these four constants, the combination epsilon 0 H square upon Me square, this will give you the dimensions of length. And then after, if we substitute the values of epsilon 0, H, M and E, and then after if we solve this one and we calculate the numerical value of this particular combination, then we'll get that is nearly equal to 10 raised to minus 10 meter. Clear to all of you? Next, 12.15. The total energy of an electron in the first excited state of the hydrogen atom is about minus 3.4 electron volt. A. What is the kinetic energy of the electron in this state? B. What is the potential energy of the electron in this state? C. Which of the answers above would change if the choice of the zero potential energy is changed? Now see, if we take total energy of electron, that is minus 3.4 electron volt. Kinetic energy, that is equal to minus E. So that will come to minus 3.4, that is 3.4 electron volt. Potential energy twice E, that is 2 into minus 3.4 minus 6.8 electron volt. Now, if the choice of zero of the potential energy is changed, then total energy and potential energy will be changed. Kinetic energy will remain unchanged, because if you change the choice for zero potential energy, then state will be changed. Clear? And kinetic energy, that will remain same one. Okay. 12.16. If Bohr's quantization postulate angular momentum equal to nh upon 2 pi is a basic law of nature, it should be equally valid for the case of planetary motion also. Why then do we never speak of quantization of orbits of planets around the sun? Now see here, if we consider the second postulate, angular momentum, that is nh upon 2 pi, then in that particular case, n value, that will be tremendous large one. In one example, we already calculated it. Okay. Now, if n value is large one, then energy calculations will give you the energies in the successive energy levels, or we can say states or orbits, that will be with very small differences. It implies that the angular momenta that we can treat as continuous one, but not discrete one. Okay, and therefore here we can't consider it for planetary motions. And one important thing that you have to keep in your mind here, planetary motions, or we can say planet, that is the observable universe. So in observable universe, the laws of classical mechanics are applicable, and these laws of quantum mechanics are applicable at microscopic level. This can't be combined. Clear? Next, the last one, 12.17. Obtain the first Bohr's radius and the ground state energy of a muonic hydrogen atom. It implies an atom in which a negatively charged muon, it is represented by the symbol mu minus, of mass about 207 times mass of electron, orbits around a proton. So mass of muon, that is equal to 207 times mass of electron. Now in the same orbit, we know this thing R proportional to 1 upon m. So R mu R upon Re, that is me upon m mu. So R mu, that is Re into me upon 207 times me. Then here you will get the radius of the orbit in which muon is revolving. Then energy in the given orbit, that proportional to mass. So we can write energy muon upon energy electron, that is mass muon upon mass electron. So E mu, that is E electron into 207 times me upon me. So we will get minus 13.6 for the ground state of electron into 207. This much is your answer. Clear?